Hi friends, today I'm going to start the third lecture on our aerodynamics course. I'm Dr. Ranjan Ganguly. Now, the first thing we are going to discuss today is the concept of Reynolds number. This is one of the very important non-dimensional numbers in fluid mechanics in general, and this number has important applications in classifying flow in terms of laminar and turbulent flow. So the Reynolds number is defined as follows. It's measured relative to a station X. So if we look at a flat plate which is there in a flow, then we have the leading edge and then essentially we have the boundary layer something like this. And let's say we go to a distance X after the leading edge and we are at that point. Now the Reynolds number at this point X is Re subscript X, and this is equal to rho infinity V infinity X by mu infinity. Now here rho is the density of air, V infinity is the velocity of air which is coming, x is the distance from the leading edge to the point at which we are calculating the Reynolds number, and mu is the viscosity of air. So if we have all these parameters, then we can calculate the Reynolds number at that given point x. Now, physically speaking, the Reynolds number is a ratio of the inertial forces to the viscous forces. So, if you look at the denominator term involving mu, that's essentially the viscosity term. And at the top, we have essentially terms which come from the aerodynamic side of the problem. For example, the density is related to the lift, drag, and so on. And this number has a great deal of importance because at high Reynolds number the flow becomes turbulent, and at low Reynolds number the flow is laminar. So this particular difference is very important because if you can calculate the Reynolds number of a flow, you can figure out what is the type of flow in those cases. Now one more problem or phenomena where Reynolds number plays a big role is in the issue of transition. And transition essentially refers to the transition of a laminar boundary layer to a turbulent boundary layer. So essentially the flow starts out from the leading edge as laminar, and what happens at some point downstream the laminar flow becomes unstable, and so pockets of turbulence start to come up, and after a certain point called the transition point the boundary layer will become completely turbulent. So that's something which happens in real life situations. Now the laminar boundary layer grows parabolically, whereas the turbulent boundary layer grows x to the power 4 by 5. So this is just the example of a typical boundary layer, which is delta here. So essentially this delta would be different for laminar and turbulent boundary layer. Now this is actually what happens in most flows, is that you first have a laminar boundary layer and then there is a transition here, and the transition takes place to the turbulent boundary layer. Now this transition point is very important because you in many cases may want to keep the flow laminar, and so therefore you may want to delay transition in those cases. So that's where the importance of transition tries to come in. Now if you want to calculate Reynolds number, let's say we take some value here x critical, then we can essentially calculate the Reynolds number at that value. So essentially if the point at which transition is taking place is x critical, then we can calculate the critical Reynolds number at that value. We already know rho, we know v, we know xcr, we know mu, and therefore from these information we can get the critical Reynolds number. So what would happen is that if the Reynolds number is at this point, then transition would take place here. So that's something to keep in mind. So now let's look at the pressure distribution around the airfoil, and that's again something which is very important. So we saw that friction in the flow causes skin friction drag, and flow separation causes pressure drag, and together these two forms of drag are important in determining the total drag which is acting on an airfoil section or on a wing. Now let us consider first the airfoil at a low angle. So today we are going to consider attached flow situation. In the next lecture I will consider separated flow. So if we look at this kind of airfoil, what would happen is that the pressure at the leading edge would be high. The leading edge is the stagnation region and the pressure in this region is the stagnation pressure. And this is also the highest pressure which takes place at any point in the airfoil. So let's look at the picture here. So this is the airfoil. Like I mentioned, the angle is very low. So essentially you get nice streamlines here. There is no separation of flow. Okay. Now we plot this graph of pressure with respect to the length. We non-dimensionalize the chord length, the x value by the chord length c. And here the pressure is given by this value here. So again, the pressure is non-dimensionalized by half rho v square, the dynamics pressure. So now this is how it goes. So what we meant by the starting value is high. This is the highest value. This is the stagnation pressure. Okay, here at the airfoil nose. Then the pressure falls like this. It reaches a minima somewhere here. And then it again goes up like this. It crosses the 0 point and here it goes slightly more than 0 at this point. So this is where it ends. Now this region here where the pressure is going up, here dP by dx is positive and this is a moderately adverse pressure gradient. So this particular pressure gradient plays a huge role in flow separation. So here of course this is a flow at a very low angle, so it is attached flow, and so therefore all the things are working out well here. We do not have flow separation in this case. Now, as the flow expands on the top surface of the airfoil, the surface pressure decreases dramatically and then it reduces to a minimum pressure which is below the free stream static pressure. As the flow moves further downstream, the pressure gradually increases, reaching a value slightly more than the free stream pressure at the trailing edge. So this is what we have been seeing in that graph, and I'm explaining it to you here. I'm going to explain it to you again because this graph is so important as far as aerodynamics is concerned. So essentially this pressure grows up here and then it reaches slightly more than the free stream value. So this is the region of the adverse pressure gradient. So you need to always remember that this is the typical pressure distribution which is there on the top surface for attached flow on an airfoil section. So what we will see later is that when there is separated flow, this pressure distribution is going to change dramatically and is going to become quite different, and that is going to be the cause of the large increase in the pressure drag. So again, today's lecture we saw the important concept of Reynolds number, how it plays an important role in flow separation, that the critical Reynolds number is the location or the Reynolds number where essentially separation takes place based on the point where separation takes place, x critical. And so some of this can be obtained from experiments and you can essentially figure out where the transition from the laminar to the turbulent flow is taking place. Now this particular transition is very important. It's a field of research. Many people spend their lives working on transition, and the reason it's very important from a practical perspective is that lot of the expenses which are incurred in flying any aircraft by any airline is due to the fuel expended to counter drag, and therefore drag is very important. And because drag is so important, you always want to minimize drag, and to minimize drag you need to figure out exactly why the drag is created. You need to develop mathematical models for the creation of drag, and if you are able to develop such mathematical models, then you can put them under optimization loops and essentially do optimization of airfoil sections. You can do optimization of the entire wing, you can do optimization of the entire aircraft, and so on. So these concepts are not only important for aircraft but for any flying vehicle, whether it be air taxi, it could be drone, it could be micro air vehicles, and so on. So essentially flow separation plays a very important role, and the Reynolds number has a very big impact on flow separation problems and so on. So I will end this lecture here today, and I will see you in a video sometime soon. See you then.